I talked about the general factoring strategy this week in class, but I wanted to just do a few more examples because we didn't have a ton of time. But the gist of factoring polynomials is you always want to first see if there's a greatest common factor, because that will always simplify the polynomial as much as we can. Then after the greatest common factor is factored out, you want to check your remaining factors to see can those be factored further. And the remaining factors you would then want to think about, well, it depends if it's 2 terms, 3 terms, or 4 terms. It will help me determine which method to use. Do I want to use a formula? Do I want to use the magic X? Do I want to use grouping or some, any other technique that you might have available to you? And then after you apply those techniques, step 3, it says to check to see if any of the factors can be factored further. And as usual, sometimes after you apply one technique, there's a new factor which you could factor even more. And you always want to think, can this be factored more? Until you run out of potential options and you run into the prime factorization of the polynomial, which is just basically you fully factored every single thing as much as you can. Just like with numbers, right? We often want to know what's the prime factorization of a number. I mean, technically 40 is 2 times 20. That is a factorization of the number, but the prime factorization is finding all of the little pieces, the littlest pieces we possibly can, that combine back together to make the original number. And there is a typo here. It should say double check by multiplying it out. Looks like I, again, need to be a little bit more careful with my documents. But let's work on a couple of these examples. So starting with the first one, step 1, I always want to factor out the GCF should there be one. And here I see a 14 and a 56. Both of those definitely have a common factor of 2. And 56 is also divisible by 7. So actually these are both divisible by 14. And after I factored that out, that would leave me with x to the 4th minus 14, 28, 56. I think that is 4. X to the 4th minus 4. Then, so that's step 1. Step 2 is to say, well, now can I factor these any further? And notice that this is 2 terms, so what I could think about is this a difference of squares? And actually, when you're looking at it, you might think to yourself, well, actually, this looks like a difference of fourths because this is x to the 4th power. And you might wonder, well, there was no formula for difference of fourths. Can those be factored? And actually, yes, difference of fourths can be factored. There are synonymous formulas for higher powers. But you don't actually need those because technically all difference of fourths are also difference of squares, meaning that I could actually just use this formula to factor it instead, because x to the 4th is x squared squared. So realistically, as you're listing it, you never want to exclude factors, so the 14 will stick with it as you continue to factor it. But the second component will factor as x squared plus 2 and x squared minus 2. And again, I know that because this, again, you could do it by the square root, because it's just going to be comprised of this is x squared squared, and this is 2 squared. So it's always the first plus the second times the first minus the second. And notice that again, will multiply out to make this. And then going any further, looking at these components, this is a sum of squares. It's not going to be factored. That's always going to be prime. And then this one is a difference of x squared minus 2. Now, technically, there is a way to factor this using the square root of 2, but most of the time we would not be using irrational numbers. And so we're okay to leave it at that. And another question you might wonder is, how far do I have to go? What's the end? And I mean, it depends on the context, because technically, if you study polynomial theorems quite a bit further, there technically is no end to factorization. You can always factor polynomials. It just takes a lot more techniques. It takes weirder types of numbers and systems. But like basically, if you don't always get, there is no such thing as the right answer. We always try to do our best to factor it as much as possible. Now looking at the next example, start off with the greatest common factor, 5x. That would leave me with x squared. And again, you might initially think this one is a sum of cubes because it's a cube, but after factoring out the GCF, we'd be left with x squared plus 25. And this actually won't factor any further because it's a sum of squares, and sum of squares have no possible factorization amongst the real numbers. Moving on to the third one, there's a common factor of 2p squared here. GCF always comes first. And after, I would be left with p squared plus 10p plus 25. And once I've factored out the GCF, I want to think about, can this be factored further? Here, it looks like we have a standard 3-term trinomial, and so I could move to the magic x. Or technically, this is what's called a perfect square trinomial. If you recognize that, there is a shortcut, but it should be pretty easy to identify with the magic x method. So AC on top, B on bottom, 5 times 5 is 25, and 5 plus 5 is 10. Notice we get the exact same thing. So here, I would be left with the factorization p plus 5 times p plus 5. And that would be that. And also, another way it is often written is if you have a repeated factor within your polynomial, in this case p plus 5 and p plus 5, you often could write this as p plus 5 quantity squared, since it's 2 of them. It's just, potato, potato, different way of expressing the answer. Looking at the fourth example, here it appears as though there is no common factor across them all, because some of them have x's, some of them have y's, but none of them have any in common. And so step 1, there's nothing, but from here, since it's 4 terms, what I would think is try factoring by grouping first of all. And if I look at the first group, I could see there's a y squared in common, which would leave me with x minus y. And if I look at the second group, I have an x squared in common, which would leave me again with x minus y. Then if I complete the grouping, I'd have y squared plus x squared times x minus y. And since the first one is a sum of squares, this one can't be factored further, and that would leave me with my final answer. Looking at the last one, this one actually is a typo, I believe, because I don't believe the x is supposed to be there. Let's just wrap it up there, because again, it looks like I made another mistake. But if you want to try this one on your own, I don't believe there should be an x there, because really there's not much to do at all.